Okay, hi everyone, welcome back to this video series on data centers port numbers. TCP and UDP must use port numbers to communicate with the upper layers because they're what keep track of different conversations crossing the network simultaneously. Originating source port numbers are dynamically assigned by the source host and will equal some number starting at 1024, 1023 and below are defined in RFC 3232 or see www.iana.org, which discusses what are called well-known port numbers. Virtual circuits that don't use an application with a well-known port number are assigned port numbers randomly from a specific range instead. These port numbers identify the source and destination application or process in the TCP segment. Figure 4.6 illustrates how both TCP and UDP use port numbers. The different port numbers that can be used are explained next. Numbers below 1024 are considered well-known port numbers and are defined in RFC 3232. Numbers 1024 and above are used by the upper layers to set up sessions with other hosts and by TCP and UDP to use a source and destination address in the segment. In the following sections we'll take a look at an analyzer output showing a TCP session. TCP session source port. The following listing shows a TCP session captured with my analyzer software. TCP Transport Control Protocol, source port 5973, destination port 23, sequence number 14563899907, ACK number 12420564456, offset 5 reserved, %00000 code, %011000, ACK is valid, push request, Windows 61320, Checksum 0x61A6, urgent pointer 0, no TCP options, TCP data area VL5 +5 +5 +5 764C 193511 2B 193511 2B 193511 2B 1935 +1 2B 19 frame, check sequence 0x0D00000F. Notice that the source host makes up the source port, which in the case is 5973. The destination port is 23, which is used to tell the receiving host the purpose of the intended connection telnet. By looking at this session you can see that the source host makes up the source port by using numbers between 1024 to 65535. But why does the source port make up a port number? To differentiate between the sessions with different hosts, my friend. How would a server know where information is coming from if it didn't have a different number from a sending host? TCP and the upper layers don't use hardware and logical addresses to understand the sending host's address as the data link and network layer protocols do. Instead they use port numbers. TCP session destination port. Sometimes you'll sometimes look at an analyzer and see that the only source port is above 1024 and the destination port is a well-known port as shown in the following trace. TCP Transport Control Protocol, source port 1144, the destination port 80, World Wide Web HTTP, sequence number 9356570, ACK 0, offset 7, reserved %0000000 code %0000010 sync sequence window 8192 checksum 0x57E7 urgent pointer 0. TCP options, option type 2 maximum segment type length 4 MSS 536, option type 1 no operation, option type 1 no operation, option type 4 length 2 OPT value, no more HTTP data frame, check sequence 0x43697363, and sure enough the source port is over 1024 but the destination port is 80, or HTTP service. The server or receiving host will change the destination port if it needs to. In the preceding trace, a sync packet is sent to the destination device. The sync sequence is what's telling the remote destination device that it wants to create the session. TCP session sync packet acknowledgement. The next trace shows an acknowledgement to the sync packet. TCP transport control protocol source port 80 World Wide Web HTTP destination port 1144 sequence number 28735807888 ACK number 9356571 offset 6 reserved %0000000 code %010010 ACK is valid. Sync sequence window 8576 checksum 0x5F85 urgent pointer 0 TCP options option type 2 maximum segment size length 4 MSS 1460 no more HTTP data frame check sequence 0x6E203132. Notice that ACK is valid, which means that the source port was accepted and the device agreed to create a virtual circuit with the originating host. And here again you can see that the response from the server shows that the source port is 80 and that the destination is 1144 sent from the originating host as well. Table 4.2 gives you a list of the typical applications used in the TCP suite, their well-known port numbers and the transport layer protocol used by each application or process. It's important that you study and memorize this table. So TCP Telnet 23, SMTP 25, HTTP 80, FTP 2021, DNS 53, HTTPS 443, SSH 22, POP3 110, NTP 123, UDP SNMP 161, TFTP 69, DNS 53, BOTTP DHCP 67. Notice that DNS uses both TCP and UDP, whether it opts for one or the other depend on what it's trying to do. Even though it's not the only option that can use both protocols, it's certainly one that you should remember in your studies. The Internet Layer Protocol. In the DoD model, there are two main reasons for the Internet Layer's existence: routing and providing a single network interface to the upper layers. None of the upper or lower layer protocols have any functions relating to routing. That complex and important task belongs entirely to the Internet Layer. The Internet Layer's second duty is to provide a single network interface to the upper layer protocols. Without this layer, application programmers would need to write hooks into every one of their applications for each different network access protocol. This would not only be a pain in the neck, this would lead to different versions of each application, one for Ethernet, another one for wireless, and so on. To prevent this, IP provides one single network interface for the upper layer protocols. That accomplished, It's then the job of IP and the various network access protocols to get along and work together. All network roads don't lead to Rome, they lead to IP and all the other protocols at this layer, as well as those as the upper layers use it. Never forget that all paths through the DoD model go through IP. The following sections describe protocols at the internet layer: Internet Protocol IP, Internet Control Message Protocol ICMP, Address Resolution Protocol ARP, Reverse Address Resolution Protocol RARP, Proxy ARP. Internet Protocol IP. Internet Protocol IP essentially is the internet layer. The protocols found here merely exist to support it. IP holds the big picture and could be said to see all, in that it's aware of all the interconnected networks. It can do this because all the machines on the network have a software, a logical address called an IP address. IP looks at each packet's destination address, then using a routing table it decides where a packet is to be sent next, choosing the best path. The protocols of the network access layer at the bottom of the DoD model don't possess IP's enlightened scope of the entire network. They deal with physical links, local networks. Identifying devices on networks requires answering these two questions: which network is it on, and what is its ID on the network? The first answer is a software address or logical address, the correct street. The second answer is the hardware address, the correct mailbox. All hosts on a network have a logical ID called an IP address. This is the software or logical address that contains valuable encoded information, greatly simplifying the complex tasks of routing. IP is discussed in RFC 791. IP receives segments from the host-to-host layer and fragments them into datagram packets if necessary. IP then reassembles data packets back into segments on the receiving side. Each datagram is assigned the IP address of the sender and of the recipient. Each router layer 3 device that receives a datagram makes routing decisions based on the IP packet's destination IP address. Figure 4.7 shows an IP header. This will give you an idea of what the IP protocol has to go through every time a user data is sent from the upper layers and is to be sent to a remote network. The following field makes up the IP header: version, IP version number, header length. Header length, HLEN, is a 32-bit words. Priority and type of service. The type of service tells how the datagram should be handled. The first 3 bits are the priority bits. Total length of the packet including header and data. Identification. Each packet has a unique IP packet value called the IP ID. If the IP packet is fragmented, the receiving host can pull it together by collecting pieces with the same IP ID. Flags specifies whether fragmentation should occur. Fragment Offset provides fragmentation and ordered reassembly if the packet is too large to put in a frame. It also allows different maximum transmission units, MTUs, on the internet. Time to live. The time to live is set into a packet when it is originally generated. If it doesn't get where it wants to go before the TTL expires, boom, it's gone. This stops IP packets from continuously circulating the network looking for a home. Protocol. Port of upper layer protocol. TCP is port 6 and UDP is port 17. Also supports network layer protocols like ARP and ICMP. This can be called type field in some analyzers. We'll talk about this field in more detail in it because it is so important, but just understand for now that this tells IP who owns the payload that the packet it is carrying, that is TCP, UDP, ICMP and so on. Header checksum, cyclical redundancy check CRT on the header only, source IP address, a 32-bit address for sending station, destination IP address, 32-bit IP address of the station. This packet is destined for options used for network testing, debugging, security and more. Data. After the IP option field will be the upper layer data. Here's a snapshot of an IP packet caught on a network analyzer. Notice that all the header information discussed previously appears here. IP header, Internet Protocol datagram version 4, header length 5, precedence 0, type of service %000, unused %00, total length 187, identifier 22486, fragmented flags 0%, 010, do not fragment offset, time to live 60, IP type 0x06 TCP, header checksum 0xD031, source IP address 10.7.1.30. No internet datagram options. The type field, it's typically a protocol field, but this analyzer sees it as an IP type field. Is important. If the header didn't carry the protocol information for the next layer, IP wouldn't know what to do with the data carried in the packet. The preceding example tells IP to hand the segment to TCP. Figure 4.8 demonstrates how the network layer sees protocols at the transport layer when it needs to hand the packet to the upper layer protocols. In this example, the protocol field tells IP to send the data to either TCP port 6 or UDP port 17, but it'll only be UDP or TCP if the data part of a data stream headed for an upper layer service or application. It could just as easily be destined for Internet Control Message Protocol, ICMP, Address Resolution Call, ARP, or some type of network layer. Table 4.3 lists some of the other popular protocols that can be specified in the protocol field. Transport layer, Internet layer, protocol numbers TCP, UDP, 6, 17, IP. Possible protocols found in the protocol field of an IP header protocol: ICMP, IP and IP tunneling, TCP, IGRP, UDP, EIGRP, OSF, IPv6, GRE, layer 2 tunnel L, 2 TP, 148, 9, 17, 88, 89, 41, 47, 115, and that's the protocol numbers. So I'm going to leave it here today for this video. If you like listening, please consider liking, sharing and subscribing. Thank you.